All right, so continuing on with the idea of polynomials, polynomials are studied extensively in math and different methods of doing that to solve some equations and understand their graphs and their representations. So rather than just having a very long lecture, this is supposed to be an investigation, but in case you weren't there to do that or you're not sure about some piece of it, one thing that you'll notice is it's really important that we have the ability to factor. That's going to be a root skill that's very important. First thing that I notice is 3x squared. It's going to have to be it's just a 3x and an x. Because this term is odd, I can't get two even values. So I know a 2 and 2 seems like a possible number, but if I put 2's there, I would get nothing but even values. And so it has to be a 4 and a 1 to do that. If you need to go with the diamond method and go with that and go through all of this process that you learned back in Math 2, it's not to say that that's not possible, but it does generate an awfully long process to go through to generate the same exact pieces of data that we got over here. I just am not a fan of that because of the time it takes. Now, in factoring, sometimes we want to look for the greatest common factor, and I notice that those both have a 2 as well as an x in it. So again, sometimes you simplify and you get partway there. It doesn't mean you're already done. So I want to double check and make sure that I cannot factor this portion of the story. And so I noticed that 2x times x would be 2x squared. And to get a 12, I think a 4 and a 3 are going to hit what I want because I have an 8x and a 3x, which would make a 5 if I did the plus and minus in that order. Now, once you have a problem factored, sometimes we'll have it equal to something, and the zero product property should be remarkably familiar to you, getting values like 0 and 2, getting values in this one like -2 and -1. Notice that there was no root from the 2 because 2 is not a variable, it's a number. However, this one is a variable, so 0 would work, as would -3 and +5. Now, some of this is going to repeat what actually happened in the first one. So each monomial in the sum is called a term of the polynomial. And a polynomial function written in this way where the terms are in descending order is considered to be in standard form. The constants are called coefficient. A sub n, which is the biggest one, is called the leading term. And a sub 0 is the constant. That's not a big deal. Now, moving on a little bit further, what I would like to do is take a look at a quick idea about some Desmos. So I'm going to go into my Desmos screen right here. Let's make it a little bit bigger. Here we go. And I had a cubic equation, and I asked us to play with those. So notice the normal cubic that we get is kind of this nice little lazy S-curve. But as we start playing with these values of B, you can notice that we can start getting a variety of other shapes. C simply moves that equation up and down. I think I missed a little piece. This should have been bx squared plus cx plus d. But some of that same stuff is still there. So you notice B pulling it around just kind of amplifies it. C does a little bit more movement left and right, and D, all it does is it moves the graph up and down. So it appears to me that I can get kind of a simple curve that has just a little bit of an S to it, or I can get sort of a hump in it. And of course, if I make A negative, it's kind of the same story, just going down, which means that it looks to me like all of the possible shapes that I could get would be a simple S-curve going up, an S-curve going up with a hump in it. This is the two cases if A is greater than 0. And the two cases where A is below 0 are the mirror images, just a simple S-curve going down and one that has a more of a pronounced curve to it. Now, coming to the second page to summarize what happened is Depending on where you put that, you could have as many as 3 roots. Again, going back to the Desmos screen, notice this graph right here has 3 roots in it. So 1, 2, 3 roots. But again, if I were to move it this way, I still have 1 root, and there's nothing that I can do. I can move it up and down as much as I want to, but it's still always going to have to cross through the x-axis somewhere. So the minimum number of roots it can have is 1. Now again, if we go a little further, how many extrema do these graphs have? So one thing that I could do is if I kind of pulled it just so, see if I can make it pull just right, there it is. This doesn't have any max or mins at all, but if I go this way, all of a sudden it has 1 max and 1 min. So it appears to me that over here, the maximum number of extrema that it could have is 2, and the minimum number is none at all. So the end behavior of this graph is if it's positive, it's going to go up on the right and down on the left. Whereas if it's a negative graph, they all had this kind of look to them like this, where it was down to the right and up to the left. And you're going to notice that those always happen in that way, where in odd cases, they're kind of up and down or down and up. They're just in opposites. Now let's take a look at that quartic. In the quartic equation, I'm going to turn the cubic off, and let's look at the quartic. So I've got ax to the 4th, etc. Let me go ahead and reset those things back to kind of their normal places-ish. Just bring them down a little bit. And let's see what the quartic equation looks like. So notice it looks like somebody did kind of a poor job of drawing a parabola where this got dented or hit in. But as we start pulling on these things, we can start creating some interesting shapes to them. And notice that you can get some that just look like a parabola with a dent, or maybe you're in here and it could create maybe even like a W shape where, let's see if I can make this a little bit more pronounced. So notice the W shape that I created. And so it appears to me that I have a variety of things that I could create out of that one. One of those shapes would just be something that looks like somebody did kind of a bad looking parabola. Sometimes we have a pronounced little wow in the curve, or maybe it's a little bit of a curve there. And then other cases where you have maybe something that looks like a W. And that's not to say that those have the same height here and here. They might or they might not. And then of course the same thing can happen upside down. We sometimes have them do this. So again, the maximum number of roots could be as many as 4. If the axis, say, went through this spot right here, it could have as many as 4. It could have a minimum of 0, because if the axis was right up here and it never even went through that, you could have as few as no roots. Now, as far as extrema, the most number of extremes that you could have would be 3, but it's going to have at least 1 extrema. And just like the other one, if the leading coefficient is positive, notice they start and end up, so they're up on both sides. And if it's negative, it starts and ends down. Now, with that, let's go ahead and see if we can do some stuff without the aid of a calculator. I notice that the leading coefficient here is negative. That's going to tell me that it's going to end down. But it's odd, so it had to start up. This one, the leading coefficient is positive, so it's going to end to the right up, and it had to also start up because they are always in agreement. Leading coefficient is negative, so it's going to be down to the right, and therefore down because evens agree. Positive leading coefficient, so it's going to end to the right up, and they always argue. Now, putting that all together, that means the maximum number of roots for any function is going to be equal to n. Whatever the maximum power is, it's going to be n. Now, if it's even, the min would be 0, but if it's odd, it has to be at least 1. Now, as far as extrema goes, the maximum number of extrema is going to be n minus 1. And again, for odds and for evens, the odds can have as few as none, and the evens have at least one extrema in there. And kind of like just putting it all together, notice whatever the leading coefficient is, that tells you what's going to happen in this story. Positives lead to positives, negatives lead to negatives, and then for odds, they always disagree with each other. And for, let's see, positive, negative, positive, and then evens always are in perfect agreement. So very, very simple little case. And moving into the back side of this thing, this is a harder one, is when you look at this, you're going to notice that we have roots at -6, roots at -3, roots at +1/2, and roots at +2. Now, what I notice is each one of these things independently has an exponent of 1. So you're going to find out that each one of these things looks like a line. I'm just saying ditto mark. They're all the same coming down. All of these are going to be looking like lines. And it's a 4th degree, so it has to be up on both sides. So the graph is going to kind of have this sort of shape to it. And so we just have to have a min in the middle there, a max in the middle here, and some kind of a min in the middle there. Now, what I don't know is how big or how small that is going to be in terms of these heights, but I know based on the 4th degree, it has to end up on both sides. And based on the powers on each one of these pieces, each one is going to have a linear piece to it. So in terms of my end behavior, if I try to approach infinity, it's going to go to infinity. And as if I try to approach negative infinity, it's going to be negative infinity. Now, this one has a 1, 2, 3, 4, 5. This is a 5th degree polynomial. The degree of this one was a 4th. Its leading coefficient is, again, positive. So I could find my zeros. There's 1 at 0. There's 1 at -1. And there's 1 out here at -4. Its leading coefficient is positive, so it has to end up and start down. The roots are at 0. Its shape is a line. The root is at -1, which should be some kind of a cubic, and at -4, which again is a line. So what I see is it's going to come through like a line in here. It's going to have some kind of an S-curve here and some kind of a line here. And so if I play connect the dots, it's going to come like this, dip back down and have it, but you should see, if you zoom in on it, you should see a little bit of an S-curve there. Now, pretty clearly, if you try to go to infinity on g of x, the thing is going to go up to infinity. If you try to go to the left on g of x, it's going to go down to infinity because it's odd there in opposite fashion. And finally, I've got a 4, 5, 6th degree polynomial. I've got 5/2 as a root of that looks like a line, a root at 0, which is a quartic, and then -3, which is again a line. And because the leading coefficient is negative, if I multiplied it, the end behavior is no matter what I do, if I try to go to either positive or negative infinity on J, both of those graphs are going to go down. Because again, since the leading coefficient is negative, it has to go down. So final answer here, I've got one root at 5/2. I've got one root at 0, one out here at -3. I said it's going to go down on both sides. So it had to come through like a line here. It had to go through like a line here, and it's going to have some kind of a flat looking parabola in the middle. So putting it all together, it's going to do something like this. Now, if you graph it, they might be a little higher or lower in there, but that's going to give you the general shape of that curve. And so that kind of gives you a little bit of an idea what it is. I'm not going to bother with those last two. You can look at them yourself. Hopefully that helps if you were not able to attend the lecture. Okay, good luck.